Okay, so this is a introduction, or I guess I don't know, a demonstration of how to use the Reef Foundation Pro test kit, which is a titration test kit that we use, or we've repurposed away from maintaining coral and using it to analyze dissolved minerals for coffee brewing. Now, I'm not the biggest fan of the TDS probe, which uses two prongs at the end to measure electrical conductivity. And the reason for this is that this probe will tell you, a number where ions are diffusing between the two electrodes, but it doesn't tell you what the identity of those ions is. So here I have a little cup of water, I'm in Cambridge right now, in Massachusetts, so this is Cambridge tap water. And I put the TDS probe in there, and it reads 357 ppm, whatever that means. Okay, so 357. I'm going to make a note of that just at the beginning here, so 357 ppm. It's important to note that that TDS probe is calibrated as if all of the ions that were in this water were actually sodium chloride. So given that we know that there's calcium and bicarbonate and all sorts of other stuff, that almost invalidates this thing for any application other than determining whether your water has nothing in it. So if you use one of these and you get a TDS of like under 100, you've got pretty soft water. Or if your water has a ton of stuff in it, which is usually bad news for whatever reason, and that would be like if this thing's reading like 3 or 400 plus, like we've just done now. So we're on 357. So the way the Red Sea Foundation Pro kit works is it gives you a variety of cards like this and then some convoluted conversions on the back. So we're going to do a series of so-called titrations. And what the idea of a titration is you're going to take a known amount of your sample that you have an unknown amount of something in it. And then we're going to add a known amount of sort of a standard, if you like, to somehow analyze what's in this water. The first one that we're going to do is the easiest one to work with, which is alkalinity. Alkalinity is a measurement of the buffering ability of water. Now, strictly speaking, that's not limited to bicarbonate only, but also all the other things that could be in water buffering away the acidity or changes in pH. But in general, the main contributor to this in coffee is bicarbonate because of the pH ranges that it acts in. So what we're concerned with is alkalinity levels that are too high because you'll get a decrease in acidity or perceived acidity of the coffee. And the way the Reef Sea Foundation Kit works is it requires you to add 10 milliliters, so 10 milliliters, I've just syringed out to get to exactly 10 milliliters of your water that you want to analyze, and you need to place it in one of these little vials here, like this. Okay. Now, what's really important now is the next thing you have to do is you're going to use the KH sort of analyte, if you like. This is the standard that we're going to be adding to this 10 ml vial. And you need to make note of your starting point, and I'll show you what that means. So we're going to take in, it doesn't really matter how much you're going to take, but let's say, in this case, I'm drawing up precisely 0.9 milliliters. So let me show you this here. So this is drawn to, it's very hard to see, I'm sorry. Here we are, drawn to 0.9 exactly. So you make a note of that we're measuring KH and our starting point, so SP is 0.9 milliliters in this case. It can be anything you want, so all I'm doing is keeping notes here. So let's just close this up for good measure and get that out of the way. It's out of the way. Now what's really critical is you go drop by drop. In aquatic environments, the bicarbonate levels can be quite high, and particularly if you're in different sorts of salt water. But in drinking water, usually these are not actually nearly as high as what this kit is made to analyze. So it doesn't necessarily take that many drops to get this thing to color change. What we're looking for is it's going to start out blue. So this red color that's in the syringe, I'm sorry, let me just adjust that. This red color that's in the syringe is going to go blue when it contacts bicarbonate. And eventually, once I've put too much of this stuff in there, all the bicarbonate is going to be used up, and the solution will then go a very faint pink. And if I add too much of this, then it will just continue on to get deeper and deeper in red. Okay, so the starting point is just one, drop by drop. So the very first drop is going to add a very faint blue color. And I'm doing it on a white surface deliberately, so you can barely even see that it's faint blue, but it's very faint blue. And then we just keep going. It's still blue. Still blue. As you can see, it's getting more intense blue color because the concentration of the dye that we're adding is increasing. So I don't know the concentration here, so I don't know what the endpoint's going to be. So we're just doing this together, if you like. Well, it's close. So as you start to mix it in between each drop, you can see, okay, we're 1 drop away now. So this is, that's it. So let's see if I can show you that that is not blue anymore. That's changed. So it was blue, and we're at the point of equivalence, if you like. I can show you, so and I'm going to make a note now. This is the point, that now you need to make a note of the end point on your syringe. So I started at 0.9 milliliters, and now I'm at precisely 0.73 milliliters. So now it's 0.73. So that means I've used 0.17, right? So that's so I can make a note that I've used 0.17 milliliters. Okay, so just make a note of that for now. We can go and do the maths later on. But now I'm going to add 1 more drop just to show you what happens if you overshoot the endpoint. So the following drop just starts to intensify the color of orange, or pink if you like. So we're already gone, so now I'm just doing it to show that this is already too far. The point in which you mark how much you've used is when the blue color dissipates, the first drop that it dissipates at. So this is beyond it. So I know that on the card, right, if you look on the card, it says that you're looking from a blue to a pink transition. But this is actually not, this transition from blue to pink actually occurs, it goes kind of white in between. So this is already too far. All right. So we're just making note of that. So that's your bicarbonate. That's done. We've made a note of how much of the standard we've used. Now it's not really good practice to put something that we've drawn out in the syringe back into the standard vessel, because now you could potentially have contaminated the whole thing, but you know, YOLO. All right, so next one. The next one I guess we can do, yeah, you have to make sure you like clean all these things at the end, of course. So the next one, I guess the easiest one here is magnesium to do next, so we'll do the magnesium one next. Magnesium actually causes the most problems for people because the magnesium sensitivity in this test kit is something along the lines of like, you know, you only got a resolution of about 20 ppm, and this is measuring as the ion. So if you've got 20 ppm as the ion, that in the calcium carbonate scale is about 80. And very few waters naturally occurring have more than 1 drop of, or more than 20 ppm of magnesium in them. So I would anticipate that this water that I'm about to titrate, if you like, is going to do the color change on the first drop. But we'll have a look. Okay. So for the magnesium one, you actually only require 2 milliliters. Now I will go through at the end as to how to increase your resolution with this test kit. But for the purpose of this, let's just do the standard to start. So you need 2 milliliters. So I'm going to draw more than 2 milliliters. I'm going to draw it up to 4, and then I'm just going to, so now I'm going to draw, it's drawn to 4, and I'm going to just go down to 2. Okay, so we've got 2 milliliters in there. It's not, doesn't look like very much. Okay, so this is actually a back titration. So hold on, you need to have, yeah, A, that's the one, sorry, they're all facing you. So we need to have, essentially you need to add one drop of this 5 times, but in between each drop you got to shake it a bit. The idea here is that what you're going to first do is bind up all of the magnesium selectively, and then the next thing that we're going to add is going to unbind it. That's the way that this works. So we need to do, oh, it's a little crusty. Okay, so yeah. So we need 5 drops of this. Now you won't observe a color change right now. This is, I believe that solution 1 is just EDTA, potassium hydroxide. There's a little of that, so it probably is EDTA. This is very exciting to watch, I'm sure. Yeah, whatever. That could have been 4. I wasn't paying attention. Doesn't matter. All right. So now we have B. We need to do 5 drops of B. And then it says we got to shake for a minute. Okay. So B. This is your dye. Looks pretty nice. Good color. So this time we're shaking this one for a minute. Okay. Good. And now we're going to look for a color change from this to purple, right? So this color to like a darker purpley color, maybe a blue color. Okay. So now we have to take up this final solution C, which is going to release the magnesium from the claws of EDTA. All right. And I anticipate that we're not going to need very much of this. All right, so it's now drawing from this sample, magnesium C. Our starting point, again, very critical with the magnesium one that you pay attention to this. The starting point here, it's hard to see. I've drawn it to 0.4 milliliters. So the SP, so the starting point is 0.4 milliliters. Okay, here we go. Now, if you guys can see that that's gone purple already in one drop. So we can make a note of that just in case you're not certain. And it looks like I'm at like 0.385, 0.385, somewhere between 0.38 and 0.39. So let's call it that. So I've used thus far. So let's just add one more to be sure that we've got there. But the point is there's not much magnesium in this water. There you go. So it's actually there. That's the end point. Excuse me. There you are. So you can clearly see a color change there. So it's actually more than what I said. So it is 0.37. Excuse me, the end point here is 0.37 milliliters. Perfect. So we used 0.03 milliliters there for this titration. Good. Okay, so we've done the magnesium one. We'll analyze that one a little later on too. All right. Now the final one here is the calcium one. This is, again, another one of these back titrations. The calcium one is slightly more complex. So this time you need 5 milliliters of your analyte water. I'm going to take up 6 to account for that air bubble. Need a little more than that. Take it to 8. Okay. Okay. We got 5 milliliters here. For the calcium one, we need to add 5 drops of A, which is this one here. Okay. So you can see everything still. So 5 drops of A. Doesn't really matter. Shake it up a little bit. Then we're going to add a reagent that binds to everything in excess. And they use the precise measurement of 1 spoonful of whatever this stuff is. It's pretty nice, okay. And I want you to shake this one for about 20 seconds now. And that's just to disperse the solid all the way through. So, pretty nice color. Okay, so now we got the calcium one, which is this guy here. Again, you have to make sure you note the start point. So you can see mine is sitting right at 0.9. Okay, so 0.9 milliliters is my start point. 0.9 milliliters. Okay. And drop by drop again. We're looking for a color change this time to something kind of like blue, if you like. And there it goes. 3. So we're at 0.84. 0.84 milliliters. Right? So that's a total used of 0.06 milliliters for the calcium. That's calcium as the ion, right? Okay. So, okay, we'll get this back in. Okay. And you can see that color change occurred relatively quickly. Okay, so to recap all of that, we have used 0.17 milliliters of the KH solution. For the magnesium, we used 0.03, and for the calcium, we used 0.06. Okay, so I'll show you this. Okay, good. All right, now on to the maths. Okay, so now we're going to analyze the concentrations and convert them into something more meaningful than simply milliliters. So let's take the first reading that we did of the bicarbonate, or the KH if you like. This one is probably the most tricky because it's reporting in sort of a fraction of a degree of German hardness, or a DKH if you like, or a milliliter or milliequivalents per liter, whatever this means. It's all very confusing in this region, but let's try and simplify it, right? So simply what we're trying to get out is the concentration of bicarbonate. And I've done the hard work for you. If you add 0.01 milliliters of our standard solution, that is equal to 2.5 milligrams per liter of bicarbonate as calcium carbonate. So 2.5 ppm per 0.01 milliliter. Given that we added 0.17 milliliters, that is essentially 17 times 2.5, which is equal to 42 milligrams per liter, or 42 ppm of HCO3 minus, so bicarbonate, as calcium carbonate. If you want to know the concentration as the ion itself, that's 53 milligrams per liter, but as bicarbonate, as calcium carbonate, that's 42 ppm. So that's the KH, if you like. That's the hard one. Then it gets a little easier here. So the magnesium one is to make this useful. The back of the cards for all of these test kits are confusing because if you note that it says titrant used on the back of the card, which means that you would have needed to have added 0.76 or something like this to make these cards even worthwhile. The only thing on the back of the card that's important here is that 0.01 milliliter is equal to 20 ppm of magnesium, and that's magnesium as the ion. So in the red at the top there, it says 0.01 milliliters equals 20 ppm of magnesium as the magnesium ion. If you want that as calcium carbonate, that's 0.1 milliliter equals 82 ppm of magnesium as calcium carbonate. Given that we used 0.03 milliliters, or perhaps maybe 0.02, or maybe even 0.01, because the error in that sort of region is quite high with these little syringes, let's just be generous here and say that we added 0.03 milliliters. Therefore, we've added 3 times 20, and what we get is a 60 milligrams per liter or 60 ppm of magnesium as the ion. To convert that to magnesium as calcium carbonate, that's 3 times 82, which is 246 milligrams per liter as calcium carbonate, magnesium as calcium carbonate. So this is actually kind of a pleasing result. I didn't know this thus far, but this is pretty good water for making coffee so far. So now we need to move on to the calcium and assess what that's looking like. In the calcium, from memory, we use 0.06 milliliters in this case. And on the back of the card, it says that for every 0.01 milliliter is equal to 5 ppm of calcium as the ion. If you want to know that as calcium carbonate, the conversion factor is 2.5. So for every 0.01 milliliter, you get 12.5 ppm calcium carbonate. We use 0.06, so that's 6 times 5, which gives us 30 milligrams per liter, or 30 ppm of calcium as the ion, which is, of course, 75 ppm as calcium carbonate. So, with all these considered, just casting your memory back a little bit, that we have about 75 ppm calcium, we have 246 ppm magnesium, and we have 42 ppm bicarbonate, which this puts our water quite high in minerals. So for flavor pulling ability and relatively low in buffering. And this is suspicious and also perhaps not such great news for boilers because if you are thinking, if you're keeping track in your mind, we've only quantified one anion, which was the bicarbonate, and we have calcium and magnesium in there at the moment, and they're in relatively high concentrations, which means there has to be another anion around, and it has to be one that's not acting strongly in the buffering region. And that is always a good indication that there's a huge level of chlorides, which means that the water here is likely going to make good tasting coffee, or at least reasonable tasting coffee, straight off the tap. But I think the boiler is going to be corroding. And actually, I've just had a realization that's why our kettle has catalytic pitting in it. There's no lime scale, but there is definitely corrosion at the bottom of our kettle. So, with all this considered, hopefully this has been valuable. If you take away anything from this, is to make sure that you use the conversion factors presented here so that you understand what one drop is in your titration set. And good luck, and send me an email if you have any questions.